Hi, my name is Oluwafunmilola Kesa. I'll be presenting our work on multiple object tracking and forecasting, jointly predicting current and future object locations. My co-authors are Olly and Victor Sanchez. Tracking and forecasting are two important tasks in computer vision. Tracking aims to estimate the locations of unique objects in a video. Meanwhile, forecasting aims to predict future short and long-term object locations in a video using the object's past location information. Tracking and forecasting are critical components for several applications, including autonomous driving, video surveillance, and smart elderly care. Due to environment complexities in videos, some issues such as identity switches and incorrect predictions are still dominant in multiple object tracking. To mitigate these issues, motion prediction methods such as Kalman filter are used to provide short-term motion estimations to refine bounding box locations. However, such motion prediction methods cannot predict nonlinear trajectories. In trajectory forecasting, a recent formulation of trajectory forecasting called MOF, multiple object forecasting, extends the traditional MOT task to predict objects' future bounding boxes. Full bounding boxes are predicted in this task rather than trajectories alone. MOF requires pre-computed tracks to estimate future object locations, which poses some challenges in MOF, such as high computational cost, and also errors can be propagated from the tracking or tracker to the forecasting network. Our contributions. Motivated by these observations, we introduced the multiple object tracking and forecasting MOTF task to predict current and future object locations simultaneously. We employed the predicted forecast in the MOT data association step in place of the Kalman filter to refine location estimates. Finally, we introduced a new step to use predicted forecast to estimate object locations during occlusion. MOTF formulation. As mentioned, MOTF is a task for multiple object tracking and forecasting. MOTF draws from MOT and MOF and follows a similar formulation to these two tasks. The input is the current frame and a sequence of past bounding boxes for each identified unique object. The output is a set of tracks of unique objects and a sequence of future bounding boxes for each identified unique object. Joint learning architecture for MOTF. Based on this formulation, we present a joint learning architecture for MOTF. JLA draws from existing architectures for tracking and forecasting. We adapt an existing model called FEMOT and added a forecast branch to the network. We use the FEMOT model as our base model because the architecture already performs detection and tracking. We train the resulting architecture end-to-end. FEMOT consists of a backbone network called DLA34, an object detection head, and a re-identification head. More details about the FEMOT architecture can be found in their paper. Forecast network. Let us look at the design of the trajectory forecasting branch that we added to the FEMOT network. The goal of this branch is to predict future bounding boxes of objects using the past bounding box information. The trajectory forecasting network consists of recurrent neural networks used to encode and decode past bounding boxes and predict future bounding boxes. First, an RNN is used to encode past bounding boxes and velocities to generate a final hidden state. Velocities are calculated by subtracting the previous location or coordinate and dimension of objects from their current coordinate and dimension, that is uj minus uj minus 1 from the previous frame. Second, in the network, a fully connected layer is used to encode the shared embeddings from the DLA34 network. Third, an RLN is used to decode the path bounding boxes and velocities from the final hidden state of the path encoder. This is to ensure that we're learning the correct input representation. Fourth, to generate future velocities, the final hidden state is concatenated with the DLA34 embeddings and passed to an RNN decoder a number of times. Finally, we use a trajectory concatenation layer to convert the future velocities to future bounding boxes. Dataset and metrics. We evaluate the performance of JLA using different amounts of training data. For the ablation studies, which can be found in section 7 of our paper, we train JLA on 50% of the MOT17 training set and evaluate the model on remaining 50%. For evaluation on the MOT challenge server, we use the same training data as FEMOT. This is shown in the table below, where we use all of the data sets to train the detection head. We used some of the data sets to train the re-identification and forecast head. The reason why we didn't use all of the data sets for the re-identification and forecast head is because identity information are not present in some of the data sets, like ETH, city persons, and CUH cases. Ablation studies. A constant velocity model and the Kalman filter are often used as baseline methods in trajectory forecasting. For a fair comparison of the JLA with the baseline methods, we modify the data association step in FEMOT to be the same as in JLA. Then, for each detected object, we generate Q trajectory forecast using a constant velocity method. Here we label that as FEMOT_CV, and a Kalman filter, which we label as FEMOT_KF. We set Q to 60, which is about 2 seconds into the future. We evaluate the tracking and trajectory forecasting performance using the metrics mentioned in section 3 of our paper, that is the CLAIR metrics for MOT and ADE, FDE for the trajectory forecasting part. JLA uses 3 components for data association: appearance embedding, fused with short stem forecast, bounding box IOU, and forecast during occlusion. We evaluated all of these components. We studied the impact of these individual components on the performance of the model. Where applicable, one or more components are turned off and the model is evaluated without the components. We achieve the best performance when all the components are turned on. Also, we study the impact of the DLA embedding, that is the image embedding that is passed to the forecasting network. We train the network without the image embedding and notice that our model performs better when the DLA34 embedding is passed to the forecast network. Sample results. Here are example tracking results from our ablation studies. The same color represents the same tracked person across the same frames. Mixed colors represent identity switches. The first row is the ground truth, which shows an occluded person in frame 340 and frame 385. The person is partially occluded in frame 340 and completely occluded in frame 385. The second row represents or contains results from the base model without forecast. The occluded target is re-identified as another person in frame 340 and lost in frame 385. The third row contains sample frames from our GLA model with forecast, and the occluded target is tracked up to frame 385. Benchmark results. We compare our method with the top methods in the MOT challenge benchmarks under the private category. The private category uses an external detector or dataset for training. As shown in Table 5, JLA reduces the ID switches compared to FEMOT considerably in MOT 16, MOT 17, and MOT 20. JLA does not perform as well on MOT 15 because the performance of the trajectory forecast is dependent on the availability of ground truth information. MOT 15 has missing tracking information during occlusion, which can result in high number of false positives. In conclusion, we have introduced a joint learning architecture for multiple object tracking and forecasting. We have shown that trajectory forecast can be used in lieu of Kalman filters to model non-linear trajectories. Also, we have shown that future predictions can be used to estimate objects' locations during occlusion. Our evaluations on the MOT challenge benchmarks show that our architecture reduces the ID switches within an MOT context considerably. Our work shows promises for future research to develop more sophisticated architectures that improve multiple object tracking and forecasting. Thank you.